Hi, my name is Shawn McCool, and some time ago, I gave a presentation at an Estonian conference called Digit, and they were so gracious as to allow me to talk about a topic that's very close to my heart right now, which is how I kind of went on a journey myself to determine, what kind of software development, what kind of tool stack do I want to use, what kind of approaches do I want to use, and like how can I think about this over a long period of time and kind of reach the potential that I'm interested in. And of course, this involves me setting context. Like I tend to build highly concurrent distributed systems, and within my personal context, I went on a journey and I experimented with a lot of different programming languages and a lot of different stacks and a lot of different software development approaches. And ultimately, I came to one that I found most compelling to me in my use cases and my values. And I want to share some of the ideas that I think are important in this space. First of all, what do I want out of my systems, right? I want really high speed, fast reaction times. I want my requests to be processed very quickly, and I want to do that for multiple reasons. First of all, the clients get a big benefit to this. If you're trying to satisfy some kind of SLA and you have an objective of feeding back a certain amount of your requests at a certain amount of time, you want it to be fast. And the more systems that are involved in like a sequential processing chain, the faster they are, all of these reaction times add up ultimately. So having a really fast reaction time is really important to me. In addition, the longer something takes to process, of course, the longer you're holding the resources open, and so the more resources you need to do the same amount of processing, basically. Second of all, and this is extremely important for me, I don't want a small part of the system to take down a large part of the system, and I don't want a user who should be affected by a problem to negatively affect a user who should not be affected by a problem. So having a significant amount of failure isolation is very critical for me going forward. I find that infrastructure can be a burden. It can reduce the amount of effort and attention that development of systems gets as you split your resources across a number of different considerations. So I want to try to make the life cycle of the system from its startup type roots where you're not sure about where all the boundaries should be, to evolving it, scaling up features, scaling up load. I want to reduce the cost of transitioning through these kind of life cycles of a software system. Finally, effective scaling is important to me. I need effective scaling is, like I mentioned, not just taking more load, but adding more features, adding more capabilities. It's in a way, scaling can be seen as another way to reduce points of isolation, points of failure, as I can spread my cluster across different regions, etc. So all of these are very critical to me, but not all properties, right? So if you want to get trade-offs, if you want to get good design, the good parts are always the opposite side of the coin of the bad parts. So you choose how to which properties that you want and which properties you're willing to give up. So one of them for me is familiarity. So I don't want, because I'm familiar with a bunch of class-based languages, because I'm familiar with this or that, I don't want to walk into a system and start making judgments about a programming language or a stack or something like this just because it's not familiar to me. I don't care how beautiful or ugly a language is. I'm not interested in this for my journey. My journey is to understand how things work and how things can work, right? I don't care how long it takes me to learn it. This is a long idea. This is the kind of thing where I'm doing this because I want to change myself and I want to change my own capabilities. I'm not interested in job opportunities. I'm not interested in the maturity of the ecosystem because, again, I don't learn this thing to solve a problem that's necessarily immediately in front of me. I can solve problems. I have built distributed systems, what I want to do is to ask, how can these things be done? How should they be done? How do I want to be able to do them in a much more significant and larger context than just, this challenge is coming up and I need to be ready for this challenge. So what that means for me is I want to learn something that's profound enough to where if I don't get a job doing that specific technology, I take those lessons anyway, and I apply them to whatever it is I do. Right. This is me saying for the next 10 years, right, I'm pursuing these ideas in order to kind of build some mastery over this idiom of thinking about systems design. Ultimately, what I decided was of value to me was Erlang and Elixir as a language built on the virtual machine. And the way that this kind of works is this. Erlang is this like kind of concurrency-first language. It's not really about being a functional programming language. It's not like trying to apply type classes and these other like lambda calculus concepts directly. It really just cares about being highly concurrent. And it does that through a variety of ways. But essentially, as you go through language design and the runtime design, you continue to make decisions that favor concurrency. And so that's kind of what Erlang is. And this is one way that it differs from basically everything else that's out there. And this is one of the reasons it caught my eye, because when it comes to concurrency, it is more radical in its model than basically anything out there. And on top, actually below the Erlang language it is running on the virtual machine. So it's called the Beam. I'll call it the Beam. I'll call it the Erlang virtual machine. And what it's like short for is Bogdan's Erlang abstract machine, or there's another name. The B is somebody's name. So Erlang abstract machine. And the idea here is that Erlang code compiles to bytecode, just like Java bytecode runs on the VM. Erlang bytecode runs on the Beam, right? And then there's another programming language that came around later, because Erlang, it's like a research project in the early 1980s. It became like first in production in 85. And Erlang came in a lot later, and it was basically like the Ruby on Rails developer was like, I really want to make Ruby better at concurrency. Then they learned about Erlang, and they're like, well, maybe I can't make Ruby significantly better about concurrency, but I can move into this space on the Erlang virtual machine and build a language that's more like Ruby, that has similar properties that the Ruby community likes, but actually has like the software engineering properties that you get from the Beam, right? And so Erlang is completely compatible with all Elixir. Elixir is completely compatible with all Erlang libraries, and Elixir is completely compatible with all Elixir libraries. So you get basically the best of both worlds. Plus, Elixir has metaprogramming and other interesting properties. And I'm really actually impressed by the leadership of the language and how it's evolving. So it's nice to be in a space where I have some confidence in the leadership. The way that the virtual machine runs is that on top of your CPU cores, it'll generate threads. It'll spawn operating system threads, and then for each of those threads, it'll have a scheduler instance. Now, all these little boxes are processes, and on the Beam, every bit of code that runs is running within a process. These processes are all running completely concurrently from one another. So think of them as like people walking around doing their own thing, but each of these processes themselves is executing code completely sequentially. So you have a lot of sequential little programs running, but they're running completely concurrently from one another. The scheduler is a completely preemptive multitasking scheduler. So it will give a little bit of compute to a process, and then it says, okay, you've had your fill, and it'll give it a little compute to the next process. So it evenly distributes the compute across the processes, no matter how big or small the work that the process wants to do. Of course, if a process doesn't have work to do, it'll just no-op, right? But if a process has a lot of work to do, it's still sharing the scheduler, the CPU time, with all the other processes. And this is why in Erlang and Elixir, you end up being able to run a significant number of simultaneous processes without worrying about like starving some of your like more active processes, starving all the rest of the process for resources. Even under heavy load, these systems tend to be responsive, right? And this is interesting to me because when a system gets under heavy load, when a system is garbage collecting and it stops everything, these are outages. As far as I'm concerned, like if we are waiting for garbage collection to finish and we are not processing a request, so the request is being stopped for half a second, to me this is an outage, right? So in the Beam, each of these individual processes has complete memory isolation from one another, and they have their own independent garbage collection. So you have like 500,000 of these processes running, and they're collecting their own garbage and they are not stopping the world to do it. It's this process is collecting garbage while this other process is not, and it collects it quickly because there's less work tends to be done in a process than a normal Java application or a Java thread or a Java virtual thread, for example. And so you end up with a system that's just responding more. Now, these processes, they don't have a way to access the memory of one another, right? These processes are as isolated in memory as any two applications on your computer. It's because Erlang, their virtual machine, is essentially just an operating system for these processes. And so what happens is they collaborate to make a functioning system, because the Erlang virtual machine, it'll spawn processes and it'll give them an identifier. These are called process IDs. And using these process IDs, a process can send a message to another process. So now we have extreme late binding, right? So what we're doing is we're saying process 1 wants to send process 2 a message. It doesn't connect to process 2 at all. There's no connection there. It tells the virtual machine it wants to send the process, and the virtual machine says okay, and it immediately returns. And it's a non-blocking call. Then the virtual machine is responsible for sending that message to the second process. So in this way, process 1 isn't blocked by waiting for the second process to receive it. Process 1 isn't waiting for the second process to process the message. It's just going along its business. And this has profound implications, which we'll get into more soon. So when the virtual machine delivers this message to the next process, it goes into a mailbox. And this mailbox is an ordered queue, right? The second process is just sitting there thinking, I could use some work. So it reads the mailbox, pulls a message, and works the message. Then it's done with its loop. It reads the mailbox, pulls a message, and does the message. Now, when it's reading the message from the mailbox, it's a blocking call. So it's sitting there waiting for a message. Of course, you can do things like time out that call. Of course, you can do a variety of very interesting things like prioritize certain types of messages. It's not important for this presentation, but the point is, this mailbox is ordered by the order in which the process received the messages, and then it processes each message one by one, and it processes that message by running a function that is completely sequentially executed. Of course, you can call out to different async code, but the point is an ordered queue, sequential execution. So this is the easiest way to think about software. To have sequential execution, right? Once things get highly async, it's harder to think about it, and you end up having things like race conditions and stuff to deal with. But having these processes be highly concurrent, running at the same time as one another, but also within them be sequential, has like these interesting ramifications for giving you as a software developer the way to choose how you want to represent your work, how you want to represent the work that the system needs to do. Now, this is my programmer art version of a function. You call the function, it's the block on the left, and then it calls the next function, and that function calls two more functions. Now, this is a very temporally coupled mechanism. So the first function call, and then the second function call, and there's a stack here, right? And they're all like coupled together. So they're like really tightly spaced gears. They rely on one another to have a coherent execution. If some part of this fails, then the entire stack fails, right? An exception is thrown. Of course, it invalidates the entire stack, basically. Now, in the Erlang virtual machine, all code runs in a process at all times. There's no such thing as code running outside of a process. So let's put this in a process. Here we have a process. And so what that means is now this process, this is this unit of code execution. It's this highly coupled temporally unit of execution, which is desirable. It's good because it's easy to comprehend, and it's a effective model for us to work with. Now, if it breaks, what happens? Well, if it breaks the process, right? The process goes away. And we end up being able to do things like this. Like, let's say we have the same function call, but we want to actually apply different different amount of failure isolation for each of these parts. So what we'll do is we'll take the parts we want to isolate from, and then we'll put a boundary in there. We'll just remove this connection. So this stops being a regular function call. Then we'll put these into two different processes, and instead of a function call, we'll send a message. This is extreme late binding, right? You send the message, you don't know if somebody's going to receive it. They receive the message, they don't really know who sent it, right? So you can send a message that the recipient doesn't even know how to process, for example, because it's late bound. And this is really, really critical for building highly resilient systems. So in this case, you say, I want to spawn process 1 on the left, and you call this function. This function is running within that process. And it says, okay, now I want to trigger the next function call, and I'm going to do it by sending a message from my process to this next process, and it does. And on each of these sides, you have these highly coupled, highly temporally coupled, tight sets of gears running, such that if one side fails, the process disappears, but the other side is fine. You've decoupled the units of failure, right? So how do you build a system that is consistent and reliable if you're just blowing up processes, right? So we have a couple capabilities that are baked into the Erlang virtual machine essentially they're ways of expressing relationships between processes and their capabilities of the virtual machine itself. So in this case, we have two processes, and let's say they're working together to do one unit of work. If one fails, then really it invalidates the work that the other one's doing. So in that case, what we do is we link the processes. This is a capability that's natively implemented in Erlang as part of the virtual machine. And if one of the processes fails, the link just pulls down both processes. And so this is a way of expressing your model of these multiple different operating things fail together. Another thing that the Erlang virtual machine exposes is the ability to monitor processes. So you can have a process monitoring multiple processes, for example. And if one of these processes dies, rather than taking down the tree, the Erlang virtual machine sends a message to the monitoring process and says, hey, this process that you're monitoring actually went down, right? And so using these tools, you can create this kind of paradigm of resiliency. It's a combination of linking, monitoring, and late binding of message passing that comes together to create this model of fault tolerance. And this model is represented using what's called supervision trees. Now, supervisor is this top process that's monitoring these other processes. Maybe we chose to express these other processes as a unit of work, essentially, so that they're linked together. And what happens is, so if one of these processes fails, maybe because they're linked, the other processes fail. And then the supervisor, it's just another process, but it has a unique role in this relationship, right? The supervisor says, oh, these processes failed. I'm going to rebuild them. And the supervisor knows what the last known good state is, or knows how it wants to reconstruct these things. So it just spawns up new processes and gives them the state that they need. And then they just keep going, right? So what the supervisor ends up being is this highly specialized kind of type of process that monitors processes for failure, and it does things to recover. And its whole job is to doing these things to recover. So your actual behavior code doesn't end up littered with as much recovery logic, because of the model here. And so you kind of separate, in many cases, some of the more functional bits from some of the non-functional bits is one way of seeing this. And it has a very interesting, it manifests a very interesting idiom for programming, because these supervisors end up being like this declarative communication of how the system should run. So what happens is, and this is from a real world example of mine, where I have a game server comes online, and what I do to start it up is I just have the game server supervisor run. The game server supervisor is fully aware that it is responsible for observing other processes. And these are the other processes it's responsible for observing: the network supervisor, matchmaking, and gameplay supervisors. It notices that those supervisors, those processes, which are just like any other kind of process, but with a specific purpose, those aren't running. So it runs them, it brings them up. And then all three of these start, completely concurrently saying, hey, the other work that's being done, the work that I'm responsible for observing is not running, and it brings those up. And ultimately, this creates the processes at the end of the hierarchy, at the end of the tree, that are doing the work. And it can, a single supervisor can observe many processes that are doing the work, right? And so you end up with this highly kind of like modular approach to resiliency, and like this networking and this matchmaking gameplay are significantly different enough that we just put them in different modules, and we want them to be kind of more decoupled so they can evolve independently. But let's imagine that something happens. So what do we do? We have a chat in our game, and we want to add emojis to the chat, and because people like emojis, let's say. So we add the capability, it works, but somebody pastes something in, and we have different character encoding expectations, and that instance of the chat that in their game crashes. Well, the way it works is they sent their client sent a chat message to this chat. The chat message pulled the message off the mailbox and started processing it, and then a fundamental assertion error occurs, and then the chat process fails and is crashed. Now, this doesn't affect the other chats, right? This just affects this one process. As a matter of fact, it doesn't directly affect the other clients either, or the network clients or anything like this, because all of the communication that's happening between the clients and the chat is with message passing, right? And so this message passing allows you to receive messages, allows you to send messages, and you're not tightly temporally coupled to these other processes such that, if an exception occurs in one, the exception blasts your system too. So this chat dies. This chat fails. All the other chats are fine. And then the chat supervisor says, that chat instance, and I know what its state was, that chat instance crashed when it was processing a message. I'm going to bring it back up and give it the last known good state. And then that chat's back online. And so what do the game players see? Well, the person who tried to send the emoji, the one that crashed the chat, it looks to them like their just message didn't go through. Everybody's still chatting on this chat. They're seeing updates to the chat. The other players just don't get that message that's broken because it was never able to be, kind of applied to the state of the chat. And their clients are sending messages to the chat, and their clients are receiving messages back from the chat broadcast or whatever. And it just, life goes on, right? So the parts that failed are gone. The other chats weren't affected. And then nobody really kind of knows that it's crashing. Nobody really kind of knows what's going on because everything just keeps working, right? Now, a more profound example of this working is what happens if the client, the part that marries the network connection with the rest of the internal game development stuff, like the lobby and the game and the chat, what happens if that crashes because it tried to do something and there was a bug in the code, or the thing it tried to do was unexpected in some significant way? Well, what doesn't happen is the network connection for that player doesn't need to be crashed, right? The network connection for that player doesn't need to be crashed. So we're maintaining a connection, and the client supervisor brings that client back up with the last good state, and the network connection is sending messages to and from the client just like it was. The network connection, like the pings and the stay alive and the handshaking and all that stuff, is nothing's changed with it. It stays still coherent and fine. And so the client comes back up and the player stays connected, right? It just keeps working. It's this radical fault tolerance that I think is one of the most compelling arguments for this runtime model, this actor model, this complete memory isolation, concurrent processes running with extreme late binding, right? This is significant to me because I don't want garbage collection. I don't want bugs to bring down the system. I want the system to just be running. If it's Sunday and some capability of posting emojis is taking a chat down when somebody tries to post an emoji, but nobody ever notices it, and so everything's actually just working, does anybody actually have to care? All that feature just isn't there. But everything else is working fine. There's nothing wrong with the chat. It's not going away. The network connections are not being inhibited. Everything's fine, actually. The feature just is gone. And this is something that I think is maybe I'm kind of a bit spoiled for now, because when I look at how at the failure models of these other systems I see or work on, to achieve this level of isolation is either so impractical as to essentially be impossible, or just impossible. When you have hundreds of thousands of these processes split over multiple cores and multiple schedulers, it's not too hard to utilize all of the resources on your instance. And you're not as much of a threat of starving some of your processes for resources because of the full preemptive scheduler. So this allows you to get more use out of a single instance than another system. You have these interesting ramifications, like, well, processes run sequentially. So what is a lock? Like if we in Java, we have a queue and it has a bunch of work, and we have a bunch of consumers running against that queue to scale up the compute and the capability of feeding through that queue, then we run the risk of resource contention. So if, like, let's say there's like a financial balance and multiple of those workers need to operate on the same financial balance, well, essentially they need to lock on that financial balance or some key or some resource that is at the right granularity level. So what that really means is that we're kind of processing things concurrently, but we take all of the work for a single resource and we make that serial. And that's what locks essentially do. But when we have these processes in Erlang that function from an ordered mailbox and do execute things completely serially, what we can do is we can model these resource entry points also as just processes. And so we don't need like these locking systems. It's like the idiom of the language is to have these highly concurrent processes, but each one is serially executed on the inside. So we have everything we need without any kind of additional weird complexity. And for things like, just caching, we can just make processes that have memory. And we don't need Redis for that specific thing. We can always say we want to leverage more sophisticated external tools like Redis clustering or whatever. We can always leverage those, but there's a lot in our development that we can do just inside the virtual machine at great advantage to ourselves and to our timelines, to our roadmaps, essentially. As we evolve the system from being a naive system to being a more scalable system, the work that has to be done at each level is reduced as well, because the idiom from day one is so strongly capable of representing some of these ideas that we tend to worry about later because there are a lot of work to do, like how we're going to scale specific things. We often get to a point in the software development where we say, all right, now we need to get to the next level of scaling, and it's time to rewrite some of our processes so that we can do that safely. And that just, it's less of a cost in this model because it's just handled. Now, when it comes to horizontal scalability, there's an interesting consequence here. We have a node, and in these nodes are processes with IDs, and they're able to send messages back and forth. They're able to send data. They're able to send functions. They're just able to send anything that could be in a data structure in the language, right? And it's all transparent. The virtual machine handles it all. If we want some horizontal scalability, we can bring up multiple instances of the application, just like any app, just like any Java app, just like any PHP or Python app. We just bring up multiple instances. We put it behind a load balancer or whatever. They're connected to maybe the same database. They're connected maybe to the same queues or subscriptions. And this tends to be how we do scaling, horizontal scalability. This model offers something a little different in that the underlying distributed virtual machine, Erlang, has a distributed clustering of its own. So what happens is that these will connect to one another, and then you will be able to send messages between processes on different nodes transparently with the same code, basically, that you would do it on the same node. And there are a lot of interesting ramifications to this. I'm not going to go into all those and all the details, but just to kind of help you kind of think through it a little bit, like there's this concept of a distributed registry where you can say, let's say I have a bank account balance and my bank account ID is 123. I can say process 2.74 represents my bank account. I'm going to register it. And then any of these other processes on other systems can figure out which process is responsible for that resource identifier by looking it up in the registry and communicate directly with that. So there's a lot of ramifications to this, and I'm definitely not paying anywhere near the full picture of it. But this distribution model of being able to transparently add nodes and transparently message between nodes has a lot of interesting ramifications as well. Now, is it what you always want to do when you scale up these systems? No, right? You can bring up more pods of the same application, have them fed off of a Kafka setup, just like you would in any other situation. But there are things you can do here that you simply can't do with these other tools, and I find that compelling. The level of software engineering in the Elixir and Erlang space is higher significantly than what I have seen in other spaces like Python, Ruby, Java, and PHP, right? So you tend to have most of the code in those spaces written by less experienced engineers, like junior engineers. A lot of the systems that are built with the Erlang and Elixir, in my experience, is closer to something like a staff engineer level. So you don't have as many packages to choose from, but what you have is really highly focused. It tends to be instrumented well. And of course, there's room for growth and room for development. Maybe you could join the ecosystem and help with some of that. But from what I've seen, not only have I been able to leverage the tools with a greater outcome and greater value than I necessarily would have been in another ecosystem. Like when I look at Java's frameworks and stuff for work, I'm not super excited, to be honest. But I'm also learning from the work that these other engineers are doing. So I find that just by participating, not only do I get better outcomes, but I learn more. So let's think about the properties I'm interested in. I'm interested in fast reaction times, and here we have a system that is suitable for near real-time system. Near real-time is like a term, so you can look it up if you want to understand what that means and how it differs from real-time. But we have processes that will continue responding, processes that are in memory, lightweight processes, take up microseconds to boot these processes up, right? And that means our systems are responsive. Failure isolation, utilizing late binding of message passing and these concept of supervision, is best in class, essentially. There's nothing else that can do what this can do. I am quite satisfied with the fact that I can start with a naive system, build it up, and as I need external tools or as I need to complicate my system with external tools, I have that option. But imagine a situation where you want to process a video and it's going to use a lot of load. You can just spin up another node of your application, cluster it, send a message across that cluster that this is the work I want you to do, right? You could even send a file handle to a handle of a file you have or something, right? You send the message across the cluster and it does the work on a different instance of compute. And then it sends the results back to you and closes itself down, right? There's a library to handle this called Flame. But this is just an example of what you get fairly cheaply and fairly easily from this model, right? It's a profound model because it has so much to offer so cheaply, because message passing offers such an interesting way to handle isolation. Now, there are things that I excluded from my search that just because I'm not interested in the aesthetics of a language doesn't mean that I did not find value in the languages that I've explored. So if you look at Erlang, a lot of people would say it's ugly. I think it's quite nice. And on top of that, I think the way that you export the functions in Erlang is very nice. And the pattern matching and the guards on Erlang and Elixir are a very different way, very optimized, but very different way to handle extraction of information from parameters. So Don't expect to walk into this and to make sense of any of it, right? Walk into it and just realize you have a long road to learn. It's a long idea. You do this for years in order to build up like a new way of thinking about things. But if you're looking to, kind of significantly evolve or significantly transcend kind of your current understanding of what's possible or ways to model things, this is a very strong move, right? Job opportunities, I don't really know about this. Like I said, it's not really one of my concerns, but I know that you're not going to find a job in Elixir as easily as you can like find a job, right? I don't really have more to add to that. Now, when it comes to the ecosystem maturity, as I mentioned, it's a bit of a mixed bag. You get higher quality software, you get less of it. The IDE integration is kind of mid, although the leadership is really interesting. We had 3 competing language server protocol implementations, and those have been combined into one official implementation that's currently like in development, and we're expecting to see some good results from it soon. There is really interesting work done on type system and type safety, although it's going to be very different from what you expect from C# or Java, right? You can't. I think it's a bad idea to move into this space and say, oh, well, where are my classes? And those are how I handle encapsulation. Those are how I handle safety. I think that's a mistake, because you don't want to be stuck in classes. This is my opinion. This is my pitch to you. You don't want to be stuck with classes. Classes are a bit of a burden. There are other ways to approach it. If not the way that Erlang and Elixir do, then the other tools instead, right? But unless you have gained some real experience doing something significantly different, you're not going to see it. So my pitch would be just play the long con, invest in the long idea, right? And so anyway, these are some resources that I think are interesting. On my website, ShawnMC.cool, I have Erlang and Elixir learning resources, all of which I've either read or watched or whatever, so I recommended them deliberately. And I would say that Elixir is the language to learn because you get all the best from Erlang and Elixir combined. And the Elixir space is where all the web stuff is. The Elixir space is where all the meta programming is. And so there's a lot of value to be in the Elixir space. So I would recommend that. Finally, I would say that there is a book publisher, Pragmatic Programmer, and I don't remember the exact name of the publisher, but Dave Thomas was like an author of the Pragmatic Programmer book, and he went and published a bunch of books. And I say look into these, and here's why. I don't traditionally recommend or even enjoy tool-specific books. I don't want to learn something like that's highly concrete from a book. I often want to learn something that's very abstract from a book. I want to learn a high-level idea that I can apply to all things, right? So this is why you read the goals, so you can learn about the theory of constraints. This is why you invest. You don't want to invest in a tool that's just going to be deprecated. But there's these series of books that are about specific tools, about the programming language, about the frameworks, about these things, and they are written by like the authors of these tools, right? The people who truly know them. So you end up with these books that are not incredibly thick, but they're quick, to the point, but more importantly, you read them and you get a good understanding of the architecture, of the idiom. And these have been really, really pleasant for me and really helped me onboard very quickly into this ecosystem and into this space. So I really highly recommend that publisher. So thanks for taking the time to listen to me. I hope you enjoyed this, and thanks for the Digit Conference organizers who really kind of set me up to have time to prepare this. I didn't present to you in this video the full breadth of the talk that I gave, but I kind of hit the highlights, right?